Hello, calculus fans. All right, we're going to talk about rates of change in the natural and social sciences. Now, I'd like to make a suggestion that in this section, probably more so than any other topic that we're going to cover in this semester, you really need to read the book and go over the examples that they have very carefully. And I would also suggest that you really need to look at a lot of the problems in this section. There's a lot of different contexts that we can talk about rates of change in the natural and social sciences. And there's really no way that I can cover all of these things with a few videos. So I think it's up to you to do a little more reading and do so more carefully than you might ordinarily. Now, in the past, we have interpreted the derivative, dy by dx, of the function y equals f of x in a variety of different ways. So first and foremost, I would say that it is the rate of change of y with respect to x. Now, this got a lot of different interpretations in science, in many contexts, and we're going to go over a few of those. Now, you'll remember that we created a change in x, which is delta x equals x2 minus x1. We've also called this an increment. Then we made the corresponding change in y, that's delta y equals y2 minus y1, which is equal to f of x2 minus f of x1. So we have an increment in x and an increment in y. Once we made those, we created the difference quotient, which is delta y over delta x, and that's equal to f of x2 minus f of x1 all over x2 minus x1. This expression that we've created, this difference quotient, is known as the average rate of change of y with respect to x over the interval from x1 to x2. Remember that it also represents the slope of the secant line that joins the points x1 f of x1 and x2 f of x2. After we've created this difference quotient, which represents the average rate of change, then we take a limit as delta x goes to 0. Once we do that, then we get this derivative, f prime of x1, and this is the instantaneous rate of change of y with respect to x. So remember that the average rate of change can be calculated just with the difference quotient, whereas the instantaneous rate of change has to be computed with a limit. Remember also that the instantaneous rate of change, or the derivative, represents the slope of the tangent line to the curve y equals f of x at the point x1 f of x1. So none of this is anything new, it's all stuff that we've been talking about. We can use the Leibniz notation to show this. So dy by dx is equal to the limit as delta x goes to 0 of delta y over delta x. Now, the concept in this section is that sometimes this function f of x will have a specific interpretation in a scientific context. And in those cases, then the derivative will also have a specific interpretation as a rate of change. And we'll look at some examples as we go along. Okay, that's all for now.